Okay, so our today's topic, the topic is inverse kinematics. Before the midterm exam, we study about the forward kinematics. For the forward kinematics, what we learned before the midterm exam were we know how to assign the frame to a robot. We know how to obtain the DH parameter that correspond to each link of the robot. And then we compose the homogeneous transform metric. And when we obtain the homogeneous transform metric, we can obtain the forward kinematic of the robot. In the final homogeneous transform metric, we can see the position at the end effector as compared to the global frame. And we can see the rotation metric that describe the orientation of the axis of the last frame as compared to the global frame. The rotation metric is 3×3 metric. And yeah, by the explanation, maybe this one may explain how the z-axis of the final frame, what is the angle, the cosine direction of the z-axis of the last frame make with the x-axis of the global frame, how the z-axis of the final frame make with the y, and how it make with the the z of the global frame. This is the y-axis of the last frame, the x-axis of the last frame, the cosine direction, and these are the position at the origin of the final frame. So today, our today content, we will begin with the announcement of the term project. And the term project have 30 points, and maybe from last week, Ajahn Pongsan already have a short introduction to the term project. As we know that for the TurtleBot, or the group that receive TurtleBot will receive the dynamic cell motor, or the group will receive the dynamic cell motor. I understand that we have the XM430, and maybe we have 2 motor for 1 TurtleBot. But in this assignment, we need 4 motor for 1 robot. And you may need to organize how can we have 4 motor per 1 group for this assignment. And of course, for this assignment, the term project, the main thing we need to do for the 4 Revolute joint robot is to obtain the inverse kinematic. In today's class, we will have the review for the forward kinematic of 1 example of the Revolute manipulator We will review how to attach frame, how to obtain the DH parameter, how to compose the homogeneous transform, and derive the forward kinematic. And the method, the analytical method to obtain the inverse kinematic in today's class, we're gonna use the inverse homogeneous transform. We're gonna use the inverse homogeneous transform. So, of course, the inverse kinematic of the robot, of different type of robot, we can obtain the analytical solution in many possible ways. But the method that I'm gonna teach you today is the method that we can apply this method for maybe the 6 degree of freedom or multiple degree of freedom robot. We may have simple robot, like just a two-link robot on XY plane. With this, if you want to go to the final XY position, you may can obtain the inverse kinematic by different way. You don't need to compose the metric. You can just compose some equation. Like you know that the x position at the end effector equal to L1 cosine theta 1 plus L2 cosine theta 1 plus 2. Y position is L1 sine theta 1 plus L2 sine theta 1 plus theta 2. And you can just try to solve this set of equation in order to get theta 1, theta 2. So that we can obtain the px and py position as we want. But for today's class, the tool that we're gonna use today is very useful in the complex problem in 3-dimensional space, x, y, z. And you need to consider the 3 rotational effect at the end effector. So the tools that we're gonna use today is based on the metric operation, and we will see how useful is the tools. And after we derive the analytical solution, I'm gonna share you one MATLAB code that I prepared long time ago. But the MATLAB code that I'm gonna show you is for 6 degree of freedom robot. But it's very, how to say, it's very easy to use. I mean, if you want to solve your problem, you can modify the program to match with your robot or any robot in the future, and you can validate the analytical solution that you obtain on a paper. Okay, we come back to the term project. In the term project, mainly we have 3 students per group, but I think we need to have one group that has 4 students in the group for the term project. And the type of submission for the term project, you need to have a presentation for the project. The content for the presentation, you need to describe how did you obtain the DH parameter for your robot. How did you obtain the forward kinematic? and show the analytical solution for the inverse kinematic. And of course, these are done on paper, but you need to apply the theory on the real robot and apply some knowledge from the part from the ROS section, and you need to be able to make the robot move, and you need to demo the motion of the robot. In order to perform this task, the thing that you need to do parallelly is, hey, you need to design the robot and you need to build prototype. But as I mentioned in the beginning of the class, that do you really want to design the robot by yourself, or you just want me to design the robot and you pick the robot and derive the parameter by yourself? By the way, we still have the score. Although you're gonna decide by yourself or you're gonna pick the robot to assembly, just assembly the robot, you have 5 points. Or if you design and assembly the robot, you also have 5 points for this part. And the DH parameter and the forward kinematic need to match with the hardware that you have. And today we're gonna focus on the technique to obtain the inverse kinematic. For the demonstration, what I expect from you is that if we have a robot with 4 joints, the revolute joint, the joint may be arranged in different possible way. You may decide to put the first joint like this so that the rotating axis is in vertical direction. You may have the second joint like this and connect to the third joint like this, and have the last joint, for example, like this. And here is the end effector. Here is the end effector. What I expect from you for the demonstration is that you need to be able to control the motion of the end effector. For example, you need to be able to draw the end effector as a line on 3D space from point A to B. Or you may want to show that, hey, your robot can draw a circle, can move the end effector as a circle on 3D space. If you want to move the end effector from point A to point B, the part of motion will have multiple endpoint positions. At each position, you need to decide the corresponding theta 1, theta 2, and theta 3, and of course, the theta 4, so that the end effector can move along the design trajectory. The trajectory can be a linear path. It can draw a circle, or it can do some special thing, like maybe it can draw a picture like this on 3D space. It depends on what you want to do. You may draw a circle like this, or draw a square on 3D space. We just focus on the position of the end effector and don't care about the orientation. Don't care the orientation, because the 4 degree of freedom robot, we can obtain we can go to the design position we want, and maybe we have one additional degree of freedom to perform some redundant or some additional task. But if you see this robot, if you put the last link like here, the last joint, the joint 4, if you put the joint 4 like here, it seems like the rotation of the joint 4, cannot make any meaning to the position at the end effector, cannot make any meaning to px, py, pc at the end effector. The rotation of joint 4 can only change the orientation of the axis at the end effector. But in our assignment, we only care about the end effector position. So maybe put the robot in this way, you cannot get the benefit of the joint 4 to obtain the position. It means that you have only 3 degrees of freedom to drive the robot to the desired position. And the joint 4 just change the orientation at the end effector. You may say that the robot don't have the redundant. If we want to go to this XYZ position, we can go to the position by like maybe the limit way to do that, because we cannot have the redundant in the robot. But they also have one advantage of putting the motor in this way, because it can reduce some complication, because for the inverse kinematic, your task is to derive theta 1, theta 2, theta 3, and theta 4, so that we can get px, py, pc at the end effector. But if you build the robot in this way, maybe you only need to solve for theta 1, theta 2, theta 3, because you know that theta 4, it don't have any meaning for the position. Okay, this is the introduction to the term project. If you have any question after this, we can still discuss about this. And in today's class, I will provide you the required knowledge so that you can obtain the inverse kinematic. In next week, we will spend more time to talk about the inverse kinematic in detail, like the next week content will be the content that I will summary from textbook. But for today, the content in today's class, I understand that like we cannot find a textbook that can provide the detail step by step like this. I try to prepare this content for you in order that you can apply for like in our assignment and for your future use. So yes, so let's begin. We begin from the content before the midterm. Frame assignment and obtain the DH parameter. Let's spend time together to recheck our concept. Imagine that in this assignment, you have dynamic cell motor. In this assignment, we have dynamic cell motor. And how can we design the part to support a dynamic cell motor so that it can function like this robot? You may need to have the dynamic cell that fit to the base. The dynamic cell that fit to the base. And in the first link, you may need to design a part to attach to the horn of the first dynamic cell. And of course, you need to try to put the second dynamic cell in some way so that it can provide the rotational axis. In this way, you need to think how can you design the dynamic cell to design the robot, and how can we extend the link length to here and have another dynamic cell motor to put to install on the next link, and have the following link. It's your task to check if you decide to design the robot arm by yourself, you can have an option, the option to change the orientation of the motor to change the twist of the link. But if you don't want to do that, I will design the manipulator for you. But you need to try to make the schematic for the robot by yourself. Okay, come back to this schematic. If we can success design a hardware that have the first revolute joint, have the second revolute joint, the third revolute joint, and the fourth one, and this is the end effector. If we can design a hardware that match with this kinematic, how can we obtain the forward kinematic of this robot? I hope that we still can remember the step-by-step how to attach frame to the robot. We may begin with the C direction. The C direction need to be coincident with the rotational axis of the revolute joint. So we have the rotational axis of the revolute joint. So the C0 is matched with the rotational axis of the theta 1. The C1 is the rotational axis of the theta 2, and C2 is the rotational axis of theta 3, and C3 is the rotational axis of the theta 4. How can we assign the X, Y axis to this? Okay, we're gonna assign the 0 frame on the floor. We're gonna assign the 0 frame on the floor. The X-axis is perpendicular to the C-axis, and the X-axis is put on the floor. And the projection the theta one, when the theta one rotate, it will change the orientation from x0 and rotate to the counterclockwise direction and change the projection by theta 1 degree. The rotation of theta 2, theta 2 will elevate the second link, and theta 3 it also elevate the link, and theta 4, the role of the theta 4 okay, we have the x0 and c0 like this, and at the axis of rotation of theta 2 we have frame 1 c1. The axis of rotation of theta 3 we have c2, and axis of rotation of theta 4 we have c3. And what should be x1? C1 is this axis. I'm gonna assign x1 in this direction. And the role of theta 1, theta 1 will change the direction from x0 to x1. Theta 1 will change the direction from x0 to x1. This direction is the direction of theta 1. The role of theta 3 will change the direction from the direction of theta 3 will change the theta 3 will change the direction from theta 2 first. Theta 1 will make the angle difference between x0 and x1. Theta 2 will make the angle difference between x1 and x2. And theta 3 will create this angle, but this angle is the angle between x2 and c3, not x3. C3 is the rotational axis of the last revolute joint. Of course, we can decide any possible x3, but in this, the theta 4, the rotation of the theta 4 will change the orientation of the x3 of the final joint that deviate from the direction of the C2. So with this, frame attachment, how can we derive the DH parameter that correspond to each link? Please don't worry, okay? I understand that you need to take time to review how to attach the frame and how to obtain the DH parameter. The goal of today's class, the main goals of today's class is, hey, if you already have this table, what is the next step to obtain the forward and the inverse kinematic? So if you still have some confusion here, don't worry, just spend time after the class to recheck the concept. But the important part of today is after we have this table, what is the next step? Okay, so come back to here. How can we compose the table of the H parameter that have 4 links? The link length of link 1 is measured. The link length is the distance between C0 and C1 along X1. The distance between C0 and C1. We lucky in this case, C0 intersect with C1. So the link length is 0. The link twist of link 1 is measured from the direction of C0 to C1 about X1. The link twist is measured from C0 to C1 by use the right hand rule about the direction of X1. So when you use your thumb point in the X1 direction and have your forefinger in the C0 and you graph to C1, we have 90 degree, positive 90 degree for the link twist. And the offset is the distance measured from origin of the frame 0 to the axis X1 and measure along C0. Origin of the frame 0 is on the ground. And the X1 is at this height. And the distance that measure along the Z0 direction. The offset for the link 1 is D1. How about the joint angle? The joint angle. The angle is the difference between X0 and X1 when we measure about the Z0 axis. X0 is in this direction, X0. X1 is in this direction. And when we measure about the Z0 or the vertical axis, the joint angle is theta 1, and we can write the joint theta 1. How about the link 2? The link 2. The link length of the link 2 is the distance between C1 and C2 and measure along X2. X2 is this line. The distance between C1 and C2 along X2 is the length L2. The twist is the angle difference between angle of C1 and C2. Angle of C1 and C2. C1 and C2 have the same direction, so the twist is 0 degree. How about the offset? The offset. Origin of the frame 1. Origin of the frame 1. Measure to x2 along C1. Origin of frame 1 is already placed on the axis of the x2, so offset will be 0. The joint angle is the angle between x1 and x2 and measure about C1. Angle between x1 and x2 measure about C1 is theta 2. The third link, the link length is the distance between C2 and C3 and measure along x3. C3 is the axis of rotation of theta 4. It intersects with C2, so the length will be 0. The twist is measured from direction of C2 to C3 and measure about x2. C2 is this direction. Measure to C3 about x2. No, about x3. About x3. X3 x3 okay, C2 is the direction here, and C3 is this direction. And we need to measure from C2 to C3 about x3. Maybe I better to put x3 in which direction should be better? Wait. Okay, I'm sorry. We need to cross from C2 to C3. We need to cross from C2 to C3 by use the right hand rule. So our forefinger need to be in the C2 and then cross to the direction of C3. Which direction should be the good direction for which axis of rotation should be good for the rotation, the grasping, I'm gonna set the x3. I'm gonna set the x3 at this point, and the x3 will perpendicular to the C3. The x3 will perpendicular to the C3, and your forefinger point to C2, and your thumb point to the direction of x3, and you grasp your finger by 90 degrees. You can get the direction of C3. So I put x3 to this direction. So now the origin of the frame 3 is also at this point. Consider the offset D of the link 3. Offset is the distance measured from O2 to X3 along C2. O2, the origin of the frame 2. X2 is this axis. C2 is this axis. So O2 is also at this point, and O2 is already on X3. So the offset will be 0. So what is the joint angle of link 3? What is the joint angle of link 3? Joint angle is measured from X2 to X3 about C2. The distance measured from X2, to X3 and measure about C2. We know that the theta 3 theta 3 is this angle. Theta 3 is this angle. And the angle measured from X2 to X3 about the axis C2 is the angle measured from this direction to this direction. We have theta 3 plus 90 degrees. Set 90 degrees plus theta 3. So this is the joint angle. We can see that if we change, we can drive theta 3 by motor, but by the frame attachment, don't forget to plus 90 degrees in order to get the joint angle, because we have the 90 degree difference between the direction of X3 and C3. And we have theta 3 that drive the angle between X2 and X3. The last link, the link 4. The link length of the link 4, C3 to C4 along X4. The direction Okay. The end effector, we're gonna attach one frame to the end effector, and the origin of the last frame, will be at the end effector position. O4 will be at the end effector position, and just set the direction of the C4 to the same direction with C3. And the distance between C3 and C4, the C3 and C4 has the same axis, so no distance between them. The link length is 0. The twist is the angle between C3 and C4. The twist also 0 degree. The offset is the origin of frame 3. Measure to x4 and measure along C3. Now we can decide where can we put x4. Where can we put x4? So let's put x4. Let's put x4 at this point. X4 need to pass through O4 because O4 is the origin of the frame 4. So yeah, X4 can be some axis that perpendicular to the C4 and pass through O4. It will be X4 at the end effector. So the offset is measured from O3 to X4 along C3, O3 to the X4 along C3. So that offset is D4. The last link, the angle, is measured from X3 to X4 about C4. If we measure about C4 and we find the angle between X3 and X4, so yeah, we have the theta 4 that creates some angle. Theta 4 can create some angle difference between X3 and X4 in any possible direction that perpendicular to the C4 and pass through O4. So we can control the angle of theta 4. Now we have all the parameter of the link from the Denavit-Hartenberg notation. Let's summary the parameter again in the new table. For the link 1, we have 0, 90 degree, D1, theta 1. Link 1, 2, 3, 4. We have 0, 90 degree, D1, and theta 1. The link 2, we have L2, 0, 0, theta 2. L2, 0, 0, theta 2. Link 3, we have 0, 90 degree, 0, and 90 degree plus theta 3. 0, 90 degree, 0, and 90 degree plus theta 3. And the last one, the link 4, have only the offset and the joint angle 0, 0, the 4, and the joint angle theta 4. I hope we still remember how to compose the homogeneous transform metric. T. One respect to 0. Okay, for the first link, cos and sine of theta 1, C1, S1, 0, 0. And cos 90 degree is 0. Cos 90 degree is 0. So this term will be 0, 0. Sine 90 degree will be 1. And sine 90 degree, and sine theta and cosine theta. So we have sine theta 1 and minus cosine theta 1. Cos 90 degree is 0. And the link length is 0. So these two components are 0. The link offset is D1. So we have the first homogeneous transform of link 1. Yes, do it by yourself to compose the link 2, the link 3, and the link 4. The forward kinematic. Okay, please spend your time to to obtain the homogeneous transform of each link and the forward kinematic. No. Before we talk about the forward kinematic, one important thing that I want to remind you, maybe from our first class, we mentioned about the inverse of homogeneous transform. The inverse of homogeneous transform. We need it for our today. Hey, T10 is equal to cosine theta 1 sine theta 1 0, 0, 0, 0, 1, 0, and sine theta 1 minus cosine theta 1 0, 0. 0, 0, D, 1. If we know the homogeneous transform of link 1, what is the 0 with respect to 1? It will equal to the inverse of 1 with respect to 0. So how can we obtain the inverse homogeneous transform? How can we obtain the inverse homogeneous transform? The first thing we need to do, is to obtain the transpose of the rotational metric. The transpose of the rotational metric. The transpose, it means we're gonna switch from row to column. It means the first row C1, 0, S1 will be the first column. And the second row will be the second column, S1, 0, minus C1. And the third row of the metric, of the rotational metric, will be the third column, 0, 1, 0. We already have this one. What about this? These are the same. These are the same. So this one is minus of C1, S1, 0, 0, 0, 1, S1 minus C1 and 0, and multiply by the P, the origin with respect to A. What is this? The origin of the frame 1 with respect to frame 0 is 0, 0, and offset D. So can we obtain this? Can we obtain this is 3 by 3 metric, and this is 3 by 1 metric, and we should expect to have something here. This is minus rotational metric of 1 per 0 transpose multiplied by P of the frame 1 origin. With respect to 0, and the position vector of the origin of frame 1 with respect to 0 is this component from the homogeneous transform. So yeah, to obtain the product of the metric. We have the row multiplied by the column C0 S0 0 D 0 0 0 0 0 and 1 D. We have D. And don't forget minus here. Don't forget minus here. And S1 0 plus minus D1 0 and plus 0 D is 0. So yes, this one is the inverse homogeneous transform of the first link. Practice by yourself from the table of the parameter, the DS parameter. From the table of the DS parameter, practice how to compose the homogeneous transform of link 1, link 2, and link 3. And practice how to obtain the inverse of the homogeneous transform because we need to use it. Today we need to use this. It's a very useful thing that we need to use. Is that clear how to obtain the inverse? We have the homogeneous transform like this. The first step to compose the inverse is to obtain the transpose of the rotational metric. The transpose of the rotational metric. The transpose of the rotational metric is nothing difficult. Just change from row. Just change from row to column. Just change from row to column. And when we have the 3 by 3 transpose of the rotational metric, the position vector here, is minus of the rotational metric transpose and multiply by the position vector of the origin frame 1 with respect to frame 0. But this vector is also simple. We can pick it from the homogeneous transform. We have minus. We have the transpose of the rotational metric. And we have the position vector here. And obtain the vector, the product from the metric and the vector 3 by 1. We have this one. And now we can compose the inverse of the homogeneous transform. Why we need this? We will see why we need this. Forward kinematic is nothing difficult, right? Forward kinematic. If you can obtain the metric, homogeneous transform metric from the first, second, third, and fourth link, the forward kinematic can be obtained from the axis 4 with respect to 0. But we have 4 metrics that we obtained from the previous step. Yeah, we may, when you practice, I want you to do like this. Of course, for the forward kinematic, we need to have this product of the 4 metric, but you may begin from the first 1. For example, here we know that the T10 is C1 S1 0 minus S1. No. S1 and minus C1 and 0 D1 and 1. I think here, if we write this as D1, it should be better. D1. D1. Okay. And for the second one, for this one, you will try by yourself, but for me, what I get is we have C2, S2, 0 minus S2, C2 and 0 and 0 1 0 and L2 C2 L2 S2 0 1. For me, when I need to obtain the forward kinematic, maybe before the midterm exam, of course, the thing that we need to be careful for obtaining the product of the metric, we need to do it by order. But sometimes you make the pair of this and make the pair of this, and you obtain the product of the total one. But my suggestion for this class, for this process, it's better to do it by order. It means, yes, let's try to obtain the T 20 and multiply by T of 32. First, 3 T 20, it means the product of the first 2 metric. T20 is the product of the first 2 metric, and you can have something here. And then the 3 per 2 will be this one. And the next step, you have the T of 3 per 0 and multiply by the last one, 4 per 3. It means that the product of this, you will get this metric. And the last one will be this one. And you can get the total one. Why I suggest you to do in this way? Why I suggest you to do in this way? From link 1 to link 4, you obtain the product of the first two metrics first, and you have this. And then you have product of the first three metrics. You have this. Because in order to obtain the inverse kinematic, many times, we need to come back to see what is the T2 per 0, what is the T of 3 per 0, instead of only focus on the final metric, instead of focusing on the final metric. Many times for the 6 DOF, we need to check 2 per 0, 3 per 0, maybe 4 per 0. Many times we need to do that. But based on my experience, we have another alternative. Here, it make the product from left to right, from link 1 to link 4. But for me, I would suggest that many times, it's more better to do from 4 to 1. What does it mean from 4 to 1? 4 to 1 means the forward kinematic. Is link 4 with respect to 0, which means we need to do 1 per 0, 2 per 1, 3 per 2, and 4 to 3. I'm gonna suggest you to to obtain the T4 per 2. No. Okay, check by yourself, but maybe and the last one. Okay, my suggestion is, hey, let's obtain T4 per 2 and T2 per 1. T2 per 1 is this one. And the 2 per 4 in this pair. In this pair, we have 4 per 2. And when we have the product of this, the last step is T1 per 0 and T4 per 1. The product of the 2 per 1 and 4 per 2, we will have 4 per 1, right? It will be this one. And then we have the total one, 4 per 0. But maybe it will create confusion. But what I want to say is many times in the inverse kinematic problem, many times we need to calculate 1 per 4. Many times we need to calculate 4 per 2, 4 per 3. Yeah, this one we don't need to, but many times we need to compute this, we need to compute this. And if during the process to obtain the forward kinematic of 4 limb, if you do it in this way, from the first 2 metric, the third one, the fourth one, you will prepare T 0 per 1, and then you will get T 2 per 0, and then you will get 3 per 0, and you have 4 per 0 by the step. Maybe, of course, we have the forward that we want, but for the inverse kinematic, many times, we need to obtain this. And we need to recalculate again. But if you want to obtain the forward kinematic and you use the sequence from backward, from this, you will have 3, 4 per 3. Then you will have T 4 per 2 and 4 per 1 and 4 per 0. Of course, you have the same forward kinematic, but during the process, you will prepare this. And we're gonna use this for the inverse kinematic. Let's see where we can use this one. Okay. T 1 per 0 inverse multiplied by the forward kinematic. The forward kinematic will be 4 per 1. Is this true? Do you think this one is correct? Do you think this one is correct? One per 0 inverse. This one it composed from 1 per 0, 2 per 1, 3 per 2, and 4 per 3. This one, the inverse multiplied by the homogeneous transform, the product will be 1, 1, 1, 1. And finally, the equation should be true. The equation should be true. But what is the benefit? What is the benefit of this equation? What is the benefit of this equation? Let's see the left-hand side. The left-hand side. Do you remember the inverse homogeneous transform? Do you remember the inverse homogeneous transform that we derived? Now, it's important here. It's important here. So I'm gonna copy this one, the inverse of the homogeneous transform of the link 1 is equal to C1 S1 0 0 0 0 1 and minus D1 and S1 minus C1 0 0 and 0 0 0 1. This one is the inverse of the first link homogeneous transform. Is this one. What is this one? What is this one? Of course, the forward kinematic will be the complicated things in the terms of theta 1, theta 2, theta 3, and theta 4. The complicated metric in terms of theta 1, 2, 3, 4. But we know that for the forward kinematic, the component of the forward kinematic will be the position at the endpoint. The position at the endpoint and the rotation metric with 9 components. The rotation metric with 9 components. And it should equal to it should equal to this one. The product of the homogeneous transform if we do from this step, we have the product of the last pair and have here, and in the third step, we have this one. You will try by yourself, but in my case, I have the T4 per 1 as one complicated metric, but if you have something in the rotation metric in the 9 component, you will try to compute T4/1 by yourself. But in my case, for the position, I have D4 multiplied by C2, C3, subtract by D4, S2, S3, plus L2, C2, D4, S2, C3, plus D4, C2, S3, plus L2, S2. And 0 and 1. From the forward kinematic step, when we want to obtain the metric of 4/0, there is one step we obtain from 4 to 1. First, we obtain this one first. And this metric will be in the form of theta 1, theta 2, theta 3, and theta 4, because this metric is obtained from the product of 2/1, 3/2, and 4/3. We still don't have 1/0. We still don't have 1/0. So in this metric, we can see only theta 2, theta 3, and theta 4 in this. And please try to complete the homogeneous transform for this. Try to obtain the inverse of the homogeneous transform, and you try to recheck the metric of this. It will be have the complicated term for the orientation, and have the position on this side. So what is the meaning of this? Why we need to obtain this one? Because this should be equal. This should be equal. But on the left-hand side, we need to obtain the product of the metric first. What is the product of these two combinations? What is the product of these two combinations? When we multiply the inverse of the first homogeneous transform to the homogeneous transform, the forward kinematic in the terms of design position, and the orientation. The product of the metric, we multiply the row to the column. So we have nx c1 plus ny s1 for the first one. For the second one, we have tx c1 plus ty s1, and we have bx c1 plus by s1, and for the position we have px c1 plus py s1. How about the second row? The second row multiplied by the first column, multiplied by the first column. We have only NC. We have TC. We have BC. And we have PC. Subtract by D1. The third row with the first column NX S1 minus NY C1 TX S1 minus TY C1 BX S1 minus BY C1, and the last one TX S1 minus PY C1. That's it. And 0, 0, 0, 1. What's important in here? What's important in here? You can make 3 equations. You can make 3 equations. But the useful equation for this step is we know that Px S1 minus Py C1 is equal to 0. So S1 per C1 is Py per Px. Do you think we can obtain theta 1? The theta 1 may be obtained from the arctan and consider the quadrant. When we know the design position in the y direction and in the x direction. When we see this, every time, please try to recheck with the physical meaning. Please try to recheck with the physical meaning. Theta 1 is the arctan 2 of the design position of Py and Px. So if we look to this robot from the top view, we're gonna see x0 and y0, and this robot deviate from x0 by theta 1. The length from the top view if we look for the endpoint position, of course, the origin of the frame 4 at the endpoint position, it can change the radius depend on the angle of theta 2, theta 3. Yeah, not changed by theta 4. But the angle that it make with the x0 is controlled by theta 1. And the position of the endpoint at the origin of the frame 4, if we look from the top view, px and py, the ratio between the px and py is correspond to the inverse kinematic. If we want to obtain the theta 1, by solving this pair of equation, the theta 1 can be obtained from the arctan of the magnitude of the position in y and in x, direction. So this is the first angle that we can obtain. So now we see that for the inverse kinematic problem, we need to find the theta 1 in terms of px, py, and pc, in terms of px, py, and pc. But yes, for the theta 1, it only depends on px and py. We can obtain the theta 1. The next one that we're gonna obtain will be theta 3. So which equation that we need? I'm gonna tell you that we need this equation and this equation. So I'm gonna use this two components and put in the blank page. We have pxc1 plus pys1. And it needs to equal to this one. So this one, D4 C2 C3 minus D4 S2 S3. And plus L2 C2. The first equation. The second equation is PC minus D1 is equal to S2C3 C2S3. Okay, and we need to solve this equation in order to get some information from this. Wow, it's not easy at this time. Okay, try to combine. Now it seems like in this one we have theta 2 and theta 3, right? But in order to make it to be linear equation, I gonna make it to be, I try to transform the original equation to be in terms of theta 2, 3, which means theta 2 plus theta 3 and theta 3 by using the property of the trigon. And do you think we can combine this? Sure, we have pxc1 plus py_s1 and cos theta 2 plus theta 3 is equal to c2 c3 minus s2 s3. So this one is just d4. C2 plus 3 and L2 C2. The second equation, PC and D1. How about this? Psi of theta 2 plus theta 3 will be psi 2 cos 3 plus cos 2 psi 3. So psi 2 cos 3 cos 2 psi 3 is just psi of angle 2 plus 3. Now we have two equations, linear equation, and yeah, we need to solve for at least we should get something. So let me think. Okay, why not we try to have the square on both sides of the equation? Have the square on both sides of the equation. It means have the square on both sides of the equation. It means pxc1 plus py_s1 square. From this step, we know the theta 1, right? From this step, we know the theta 1. So we know sin theta 1, we know cos theta 1. And px and py is our desired position. So we should know px, py is our input to the problem. the right hand side of the equation, we have d4 square c23 square plus 2 L2d4 c23, and the last term L2 square c2 square. The second equation, we have PC, which is our input, D1, the constant from our robot parameter, D4 square, S23 square, plus 2 L2 D4, S2, S23, plus L2 square, S2 square. Try to combine these two equations. On the left-hand side, we have Px C1 plus Py S1 square, and we have PC minus D1 square. We know everything for the left-hand side. We know the position that we want. We know the sine and cos of theta 1. We know the robot parameter D1. How about the right-hand side? Cosine square plus sine square is equal to 1. So D4 square and L2 square, because this will equal to 1 and this will equal to 1. How about this? We have 2 L2 D4. We have 2 L2 D4, and we have C2 C23 plus S2 S23. Can you get some hint from here? This is the cosine of the angle difference. This one is cosine of theta 2 plus theta 3 subtract by theta 2, which means this one is just cosine of theta 3. It's just cosine of theta 3. So you can rearrange the equation so that you can get the cosine of theta 3. This term is equal to cosine of theta 3, because this one is cosine of theta 2 plus theta 3 and subtract by theta 2. So yeah, it's theta 3. So from here, the cosine of theta 3 can be obtained by rearranging the equation. We have Pxc1 plus Pys1 square plus Pc minus D1 square, and subtract by D4 square plus L2 square. And when we divide all of this by 2 L2 D4, we have the cosine. Luckily, we know that sine should be equal to square root but if we have one cosine, we know that cosine of theta 3, we have the closed form solution for the cosine of theta 3. In order to obtain the sine of the theta 3, we use the trigon property, but there are two possible ways to get the sine of theta 3. We have the positive and negative value of the sine of the theta 3. So do you think which one we should use, the positive or negative sine of theta 3? So it depends now. It depends. Of course, we can use both the positive and negative value for the sine of theta 3. Now theta 3 is the angle that control. Now theta 3 is the angle, this one. Sine theta 3 will be positive, and sine theta 3 will be negative for the different posture of the robot. You need to separate the case in your workspace. If your robot need to reach something above this position, this offset D1, you may likely to have the sine to be positive. Or if it need to reach something lower, you need to use the negative case. But yeah, the endpoint position is important. The design orientation is also important. And when you write the program to solve the inverse kinematic, you begin with theta 1. You obtain the theta 1 first. And for theta 3, we have two possible ways to get the theta 3. The cosine is fixed, but the sine of theta 3, we have positive and negative possible value. So yeah, in your program, you need to put the case for this. Maybe if you want the robot to move the theta 3 just to the upward elevation, you're gonna take it to be the positive value. If you want it to like move the arm down, maybe sine theta 3 will be negative. It depends. But yeah, after select the case that we want and match with the algorithm of the robot, finally the theta 3 is the arctan 2 of sine theta 3 and cosine theta 3. Now we solve theta 1, solve theta 3. The last angle we need to solve is theta 2. How can we obtain theta 2 for the inverse kinematics? in this in this I combine the theta 2 and theta t together because it seems to be easier to solve the equation, the set of equation. We can reduce the number of terms. We can reduce the number of terms, and we can separate the unknown term easily. But for now, we already know we already know the theta 3, which means we can consider C3 S3 as a constant because we know the theta 3 is already a known variable. So I'm gonna use this equation again. But now we know theta 3. And I will try to solve for theta 2 from these two equations. So we're gonna use the equation again, but we're gonna leave it in this form because it's easier than combine theta 2 to theta 3 because now we already know the theta 3. Px c1 py s1 d4 cos minus psi and pc minus d1 is equal to d4 of psi 2 cos 3 plus cos 2 psi 3 and L2 S2. Okay. So we already know the theta 3 and we want to solve for the theta 2. It should be good if we begin from try to separate the term psi and cosine. Try to separate the term psi and cosine of theta 2. So separate the term psi and cosine of theta 2. C3, we already know the value. And have the theta 2 this equation. Again, we will try to separate the term psi theta 2 and because we know the zeta 3. Okay, can we solve these two equations? Can we solve these two equations? Let me think. Okay, we have equation 1 and equation 2. We will multiply the equation 1 with D4C3 plus L2 divided by D4S3, and then we'll plus by equation 2. Can you imagine if we multiply the equation 1 by this term? Okay, we will multiply the equation 1 by this. First, we have D4C3 plus L2 divided by D4S3 and multiply by PXC1 plus PYS1. Although this is long things, but everything here we know. If we put it in the computer program, it's not a big deal. We know all the length of the link parameter. We know the zeta that we already obtained from the previous step. We know the position we want, we know the zeta 1. So in the computer program, if you need to calculate every time, it's not a big deal. Okay, for the right-hand side, if we multiply this to the first equation, what we have is we have D4C3 plus L2 and square and divide by D4S3 and C2. And for the second term, if we multiply this to this, it can cancel this one. And we will have D4C3 plus L2 and multiply by S2. So now what's gonna happen if we combine? Okay, let's say this is the equation 3. Sorry. What happens if we combine equation 1 and equation 3? If we combine equation 1 and equation 3, yeah, to the left-hand side, it still be a stupid long thing here, but D4C3 plus L2 divided by D4S3 PXC1 PYS1 and plus PC minus D1. We combine these two equations. For the right-hand side, we can cancel the plus and minus, and we still have only C2 available from these two terms. We have D4C3 plus L2 square divided by D4S3 and plus D4S3 and multiply by C2. Yes, finally we can obtain C2 because we know all the numerical value of this We know the numerical value of this. Now we obtain C2. And S2, again, S2 can be obtained from this. We need to come back to check C2. The condition for C2 is the same with the C3. If psi of angle 2, theta 2 will be positive, psi of theta 2 will be negative. The case that we need to put for this, we need to separate the case in the program. And yeah, in today derivation, we know how to, the guideline to obtain the numerical value of the inverse kinematic. In next week, I think we're gonna learn something that can teach us to be, how to say, when we need to make a decision, what should be the positive or negative value of the psi theta 2 and psi theta 3 when we need to prepare a program. Hey, in which case we need to select the positive, in which case we need to select the negative, so that the robot can operate smoothly and not crazy during it transform from negative zone to positive zone. I think from next week we will study that, but today I think it's too heavy for you. And yeah, please spend your time to recheck the concept, how to obtain the inverse kinematic. You see that actually we need to find theta 1, theta 2, theta 3, and theta 4, but I'm not talking about theta 4 because it's not affect the endpoint position. Although the theta 4 will be 0 or some angle, it doesn't change the endpoint position for this robot. So please spend your time to follow today's class content and begin thinking about your robot and make decision. Maybe it should be better. I mean, I don't want to force all of you to think in the same way. You will make the group first. If your group decide to have a robot that I prepare for you, I will design the robot and give you a part. The challenge will be my robot not gonna be easy, and you need to try to have the mathematical description for that robot. The second choice for you is your group plan to build a robot by yourself. You have an idea, have the cat for a robot. You show me the cat. We discuss about the production of the part. I make the part for you and you build your robot. And of course, you already know the parameter and the math for your robot. It's also possible. So that's the assignment for today. Do you have any question?